Now, linked lists are a type of data structures. Now, in modern computer applications, data can be stored in various forms according to the problem we are trying to solve. Generally, when we start programming, we use the language data primitives like integer, strings, and then we come to arrays. Now, arrays is like the first. In arrays, we store data sequentially. Like if I have an array 1, 2, 3, the data is stored sequentially. It's a linear data structure, meaning if we traverse through it, we'll go from one to the next to the next. Now, why do we need data structures different from what we already have been using or have like arrays and stuff? It's because of memory allocation. In most programming languages, in some programming languages like C++, we have to explicitly mention the memory we are allocating to the array. In languages like JavaScript or Python, we don't have to. That there's a certain level of abstraction that hide it from it, but still memory plays a huge amount of role in the performance of an application. Now for arrays, let's assume we have like this is our memory block, and we have memory blocks inside of it. And let's assume that these memory blocks are filled. They have like data stored in them. Now when we create an array, let's say this one, 1, 2, 3. Now array is a static data structure, static memory allocation. That means that it will require proper 3 blocks. Since we have 3 elements here, proper 3 blocks to store it. That means that if we have this memory block over here, we cannot store our array elements here. We'll have to store them sequentially. Like we have to get 3 blocks of free memory space. Now assume that we have these memory taken up as well, and we have this taken up as well. Now we just cannot simply store the array because we are like, you know, this is taken up as well. Now we cannot simply store the array because we don't have 3 free space, 3 contiguous block of memory free. Whereas in whereas in linked list, we do not. Linked list is a dynamic data structure, dynamic memory allocation, meaning it will take whatever memory is free because the elements are arranged differently than in an array. The way we store data in a linked list is a bit different. We just do not have the data thing. We also store the address of the next node. For example, let's say we have a linked list which stores age numbers, right? So let's say 38. And here we store the address of the next node. Let's say that this node is at, the address of this node is this. It's just for the sake of explanation. And here's somewhere node 170, and here's somewhere 220. So here we can store the address for the next node 170. Here we have our one node and our other node. We can store the data in here, let's say 22, and the next node is 220. Here 10, and the next node we don't have any node, so it's like it's the end of our linked list, so it's not. So basically at this we store the data and the address of the next node. So you can say that this is connected to this. Just create it a bit like this, and then from here it's connected to this, and this is our linked list. Now despite of not have, now even if we don't have a contiguous block of memory, we can still add, we can still create a linked list of 3 elements. Now before going on into the addition and deletion processes, we'll see how to create a node in JavaScript programmatically. Here we are on a code base. Now we'll create a class of node. This will store the required information. Now as we know, there are 2 kinds of values we need. We'll create a constructor function. We need a value. Now we created a constructor with a value function which will the data part of the node, and then this dot next will take the address. It's defined by default to, it's set to null by default, and we can also set the value to null by default. Then we can create a class of our linked list. Going back to our original list, the list always starts with a head node. In our case, this will be the head node, and this will be the tail of the list. So starting from the head node, meaning starting from 100, we can then traverse. If we know where the first element is, then we can traverse. If we know that the first element is at the 100th, then we can use the next node parameter to go to the next node and the next node, and since it's null, it's the end of our list. So we'll add a head node in our linked list constructor function. By default, it's null. So now we can create different functions that a linked list requires. Like array has their methods, so linked list also had methods like appending a value to the end of the list and prepending a value to the start of the list, and inserting at a certain position or finding a certain element. So we'll create some functions. So first function would be to append, basically append a value at the start of the list. Prepend, append a value at the end of the list. Append at the end and prepend at the start. Then we'll have a size function. This should be set as a getter because we'll use this as a property. We just need the size, and then we can have like get the head node and get the tail of the list. Then we can have a function like get the index, get the value of the length of the node at a certain index, pop an element from the end, check if the linked list contains a particular element, and find a particular value, insert the value at a particular index in the list, and remove a value at a particular index. We are also creating a print list function in here, just when we'll be using the list at the end. When we've completed all these functions, we can easily visualize the list. So these are the functions we'll create. Now, how do we end or remove elements from a linked list? Let's say we have to, this is the index 0, this is the index 1, and this is the index 2, and we have to add an element at index 1. Basically, we'll have to shift all this. This will become index 2 and this will become index 3. So how will we do it? It's just as simple as adding, is just changing the next values. So we'll create a new node. Basically, we'll create a new node first. This will add the value whatever it is, and we will now traverse the list. Now head it as 0. We have to add the element after this, since at the first index. So what we'll do, we'll change the address of the next node that is here to the address that our new node is. Let's say it's something like 350. So we'll add 350 to here. Now this pointer will now point to this node, and the next value here will add 170 to here. So now this node will point towards this node, which was earlier the node at first index. Now the indexes will be like this: 0, 1, this would be 2, and this would be 3. Now to remove an element, we just simply, like, let's say we have to remove this element, the element at second index. So we'll just change the address of the node of the previous node of this element. We'll change this to the next node of this element, which is 220. Now instead of pointing towards this node, it will point towards this node. This is how we can remove this particular node out of the linked list. Now we'll code this out. We'll start with our appending function. We'll create a new node. We'll give it a value, the data stored, and now we have to first check that if the head exists, meaning it's not a single, it's not an empty linked list. It's not if this dot head does not exist, meaning if this dot head does not exist, meaning that it would be the first element in our linked list, so it would be this dot head itself. So this dot head would equal new node. Simply return. But if that's not the case, it's not like the linked list is not empty, then we will traverse through the list, starting with this dot head. We will traverse and we'll reach the end. As long as there is a next element to the current node, we'll change the current node to the current node's next element. So at the end, we will have the current node will store the node which is at the end of the linked list. So we can simply use the last node. This would be the last node after this traversal. Current node dot next would then equal to our new node. Now for prepend, that is adding in the start, it is easy. We just have to, like, first we create a new node obviously, and then new node dot next would equal to this dot head, and this dot head would equal our new node since we are adding it in the front of the linked list. Now to get the size, we'll have to traverse the list. We'll start with a counter variable, and then we'll traverse starting from the head, of course, while there is a node. we'll increment our counter variable, and we'll move to the next node, return the count. And the get head node is as simple as returning the head of the list. For the tail, again, we will traverse first, select current node, starting with the head, and we'll return the last node. Now here we have to check if this dot head exists, because if it does not exist, meaning it's an empty list, so we'll just return null because there's no tail since it's an empty list. Now to check if like what element is at the particular index, so we'll traverse again. The traversal code is mostly the same. We will just traverse until we reach the index. Now if there is no current node, meaning we reach a point in the until the index that there is no current node, meaning that we have reached the end of the list and there is no element at that particular index because it exceeds our length, the length of our list. So else we'll continue traversing, and when we'll get to the index, we'll have the node at that index, so we'll return that. And also here we have to check whether the index is less than 0, because then we'll have to return the. Now the pop function, it just removes an element from the end of the list. Now again we have to check if the list is not empty, otherwise if it is empty then we'll return none. And then we'll have to check if there is just one, meaning there's the next, this dot head dot next exists, meaning there is another, meaning there is no other element besides this dot head, then we'll just have to return head. We'll get this dot head, and since pop removes the element as well, so we'll set this dot head to null, and then we'll return the popped element. Else we'll have to traverse, obviously. Now again here we'll have to look into next, like twice, the next to the next element of the current node, because we'll have to set the current node's next to null. Now when we'll reach the last index, we'll reach the second last index and not the actual last index, because this is because of this particular statement. Then we'll get the element, which will be the current node's next, because we are on the second last element, and the current node's next is set to null, and we'll return the pop. Now similarly we'll write the code for contains and find value. I'll just write it quickly. Now the most important functions of inserting at a certain index. So first we'll create a new node. Now if the index given is 0, meaning it is the head of the linked list, the new node's next becomes the current head value, and start head becomes new node. We can simply return. Now regarding this situation, first have to check that the index shouldn't be less than 0. We'll just simply return in this case. Next, if we have to insert it in the middle or somewhere, then this dot will traverse, obviously. Again, we don't have to go to that particular index, we just need to be at the previous element of that index, so that we can change the next addresses if current node exists. I mean if it doesn't exist. Now in this case, the current node now stores the node that is previous to the index we want to insert at. So we'll current node dot next equals to current node. I mean new nodes next to the current node dot next, and then current nodes next would equal the new node. Similarly, we'll implement a remove at function, just like we saw. First, we'll check the index if it's less than 0, or if it's an empty list, we'll simply return. Again, if the index points towards the head, we'll simply this.head would equal this.head.next and we'll return. So this.head value would just disappear. Then we'll traverse the array as in previous. Again, we need to take the element before that particular index. Now, if current node.next exists, there's an element at that particular index, then we will remove that element by changing the address that the current node is pointing to the next of that element. We will just need a print list, a function to print the list. I'll write it just quickly. This is for demo purposes. Now we have implemented all of our functions. It's time to create an actual list. We'll create a new linked list. And now we'll begin by adding elements. We can append the age, place like 38, 22, and 27. For our list, we'll use the function. Just change. It's just a bit of Python here coming along. Now if we'll run a function, yes, so as here you can see, our list, the first element is 38, the second 27, then 27, and then it points towards null. Let's say we want to say L dot the head node. Okay, and we get the head node value 38, next node value 29, and next node value 27, whose next is null. So the node that returns is the head node is as a value 38. We can just simply write the value 38. Now let's say we need to include some element. Well, it's 38, 22, and 10 was our original list. 38, 22, and 10. Now we need to insert the value 27 and 1. Okay, once we have inserted, we'll again print the list to see the changes. Here you can see 27 is inserted. This was our original list, and 27 is inserted at this value. So here we can work out the different functions, and this was linked list. Thank you for watching.